Welcome. This is also continuation of our earlier discussion, that is the mechanical properties of ceramic materials. We have earlier discussed different concepts of different techniques of measuring different properties of mechanical properties of ceramic materials. Also, we have started discussing how to measure the fracture toughness. The fracture toughness of ceramic material, that is one of the most important mechanical property of ceramic, or particularly to understand the fracture mechanics or fracture of ceramic materials. We have just introduced in the earlier lecture these two techniques, the indentation techniques, the indentation microfracture method or IM method, and then indentation strength bending method, ISB method. So, in the first case we have just indented, generate an indent with a diamond indenter, and then apply the load in such a way that not only it creates an indent of a permanent deformation, but also create a crack, because the load is enhanced, so that a crack is created. Now, there are two situations here. This is the side view and this is the indent. This is the indent, diamond indent which you have generated. This was at load. Initially this was at low load, when only the crack has been generated here on two surfaces, okay. Whereas at higher load this crack has propagated, in this manner, right. So, here you can see this is the crack length C is the crack length, this is a smaller, sorry I made a mistake, this is smaller crack length, this is a larger crack length. Okay. Now, we have already said that for making a indenter, you have to polish the surface. Of course, initially the surface was polished, but the crack was internal. Okay. From the top surface you may not see the crack properly, and that is why you have to once again polish that surface to see the exact nature of the crack, the exact way the crack has propagated. So, as you can see, this appears to be straight initially, but inside you will see a bend cross section of the crack. So, after polishing, which you will be evident here, and this is at a lower load, this is not a higher load, and that is why you can see this distance is this size is slightly larger, and this side is also slightly larger, and you have to measure these crack lengths. Okay. You have to, this is your C, and once you measure the C, and then you measure the A also. A is this distance, the dimension of the indent. Here also it is A and this is C. So, the crack has propagated not only in this direction, but it has been joined together, okay, because these are the four stress intensifying centers. The stress at these corners are very high. So, the cracks will generate here, and then finally, in the bottom at the below the indenter they will join. So, the crack will join like this, and that is what you can see here. Oh, before that, this is the cross section, this is the formula which we have to use by measuring the value of C, and then find out the value of H the viscous hardness, and A and C you will find phi is a constant based on the crack geometry, and H is the viscous hardness in GPa, and f is a function of c and a defined above. Okay. So, that way we have find out from the just by indenting, you do not have to make a fracture, complete fracture of the sample, what we have done in the notch test. In the notch test, the sample is fully fractured. Here it is not fully fractured, just by making a indent you can make the you can have a measure of the fracture fracture toughness. Of course, there will be a lot of difference. There will be some difference between the fracture toughness obtained by the other technique and these techniques. In fact, all the techniques will give you slightly different values of the fracture toughness, that also you have to remember. There is another a combination of indentation and fracture, that is also possible, and this is what it is done. First of all, the sample there is a indent is made on the surface, and then you put the surface upside down and they then do a 4-point bend test. So, the indent is here, indent has been created by this indenter. A silicon oil is placed primarily to protect the indenting surface from the atmospheric contamination and atmospheric effects. Okay. So, so after the indent is formed, so it is a combination of both fracture. So, as if we are making a notch by indenting. So, this notch has been created by indenting, and then this notch kept upside down and do the 4-point bend test. Now, this is the crack propagation area below the indent. Okay. There are two different areas of cracks or the stress concentrations. The stable crack growth, this region is the stable crack growth, and this is the radial crack growth. Okay. These two regions can be separated, or there are different type of stress concentrations are there, and therefore, one can have once again an expression of indentation strength bending by this method. KIC is this expression. Okay. So, where eta is a constant with an approximate value of 0.6, sigma is the fracture strength, E is the Young's modulus, H is the Vickers hardness, and P is the indentation load which have been added, which have been used or applied. So, by that method also one can find the fracture toughness. Another simple expression for the fracture toughness is based on the again measurement of extended crack length cm, and where this is again an expression using, instead of c is used a cm, which is an extended crack length, where a and b are constants with approximate values of 2 and 0.68 MPa per MPa meter square, or meter to the power half, not meter square, meter to the power half respectively. So, basically what we are saying, there are different techniques of measuring the indentation hardness, the fracture toughness. So, either by making a notch or making an indent, and or the third one is making a indent followed by fracturing the sample. Well, with these different backgrounds, we can look at some of the common materials, common ceramic materials having different properties, and what is the just range of properties. This gives you some range of different properties of ceramic materials, so far as the mechanical properties are concerned. Al2O3, that is the polycrystalline Al2O3, this is the value of Young's modulus in GPa about 400. KIC, this should be not small, this should be capital I. 1 minute, I will just correct it here. Right. So, this is the KIC value, of about 2 to 6, normal Al2O3. Hardness is about 20 to 25 GPa. Silica or in the quartz, single crystal quartz, we have 95, the KIC value is not here, and this is about approximately 12. Magnesium oxide, the Young's modulus is much larger, not much larger, it varies depending on the preparation condition, but lower than that of Al2O3. KIC value is almost same, maybe in the slightly lower side, and then hardness is also low. Zirconia, you have two different forms of zirconia. One is stabilized zirconia or cubic zirconia, that has Young's modulus 200, and there is partially stabilized zirconia also, not fully cubic zirconia, partially, that is a mixture of two partly cubic zirconia and in which you have a tetragonal or monoclinic zirconia. So, that is also Young's modulus is more or less same 200, but one can see that the partially stabilized zirconia has a much higher KIC value. It of course, the range is also large, it is only 3 to 4, whereas it can go up to 15, which is a very high value, but it can be as low as depending on what is kind of microstructure, how it has been prepared, and what is the size of the second phase and so on. So, it varies, but it is possible to make a very high PSZ or partially stabilized zirconia with very high fracture toughness, and in fact, we will come back to this material later, that sometime people say it is the ceramic steel where having the highest fracture toughness. The hardness is more or less in the same range. Beryllium oxide, the fracture toughness is not there, but its very hardness is low, it is a soft material, but Young's modulus is fairly high. Sorry. Magnesium aluminate, spinel, which is also being used as a very important refractory these days, and there are many other applications, engineering applications, and this is 250, the KIC value, that is the fracture toughness is not so high, the hardness is more moderate. Mullite 230, 224 again, and a moderate hardness, okay. But most of them are in this range 15 to 20, 25 maximum you can get here. Silicon nitride, hot pressed silicon nitride is one of the most important structural ceramics for engineering application, particularly high temperature engineering application. Sorry. I will change this also. Both silicon nitride and silicon carbide, they are known for their high strength at high temperature, particularly silicon carbide, and as you can see their Young's modulus is also fairly large. They have a fracture toughness which is on the higher side, and silicon nitride in particular can be made a much tougher material, or KIC value can be improved by control of the microstructure and preparation condition, and these are the hardness values. B4C, that is boron carbide, is supposed to be very strong material, and you can see its Young's modulus is also fairly high. Unfortunately, the KIC value is now available here, and 30 to 35 is the hardness. Similarly, another non-oxide ceramics, aluminum nitride has a Young's modulus of this and hardness of this, KIC value is not there. Sorry. Titanium diboride a very high Young's modulus, one of the hard materials also, and it is used for many high temperature applications. If the time permits, we will discuss some of them. Titanium carbide, once again a high Young's modulus value, and then KIC value is moderate, and hardness is also of the same range. Tungsten carbide is a widely used ceramic material for various different applications, and you have a high Young's modulus. This has a fairly high fracture toughness, okay, fairly high fracture toughness of 6 to 20, one of the highest one can say. Zirconium diboride is also of the order same order of the Young's modulus as the others, and hardness is also in the same range. Fracture toughness value unfortunately is not available. So, this is just to give you an example of different mechanical behavior or mechanical properties of some of the important ceramic compounds. Many of them are used industrially and for many different engineering components or many engineering purposes, including of course refractories. Now, this is we have discussed the properties, we have discussed what is the property means, like what is fracture toughness, how to measure it, and so on. As you have seen in the list just presented, that fracture toughness of most of the ceramic materials are not very large or very high compared to metals and alloys. They have a very high fracture toughness, and that is one of the weaknesses of ceramic material, right. They fracture quite well, fracture very easily, and not only that, when they fracture there is a catastrophic failure. So, we have to see whether it is possible to make this ceramic material little more tougher. Sorry. So, we let us consider, is there any toughening mechanisms by which some of the ceramic materials can be made more tougher and more suitable for engineering applications. Unlike in metals and alloys, dislocations are not active in ceramic systems, and consequently there is hardly any plastic deformation that we have discussed time and again, that the role of dislocation in ceramic materials is very negligible. Even if it is there, they are not that operative, and it is the existing cracks, finer cracks, which actually is the weakest link, and they are the primarily responsible for the fracture. Toughening of ceramic system is possible only by restricting the propagation of the existing cracks, which may be attained through the control of microstructure, particularly in the vicinity of the crack tip. So, in metals and alloys, when you try to toughen or strengthen a ceramic material, primarily we restrict the movement of the dislocations. Okay. We put some obstacles on the path of the dislocation movement, and thereby one can restrict the deformation and also strengthen the material. That is the basic principle on which the strengthening is done in metals or alloys. However, as just mentioned, the dislocation do not take a very important role, or dislocation movements are not of that importance in fracture of ceramics. It is actually beyond the dislocation movement. It is a sudden fracture, or the cracks already gets generated in the material, and it is the propagation of the crack which has to be restricted if the materials or the ceramics have to be strengthened further. So, the fracture toughness of polycrystalline ceramics is significantly higher than that of single crystals. Okay. Similarly, fracture toughness of glass ceramics is much more than that of virgin glass. So, this is what it boils down, or what it is a consequence of how to restrict the movement of the cracks or propagation of the cracks. If you have a polycrystalline material, there are grain boundaries, and these grain boundaries in fact impedes the propagation of the cracks. So, if it is a single crystal, then there is no such grain boundaries, and once a crack is generated because of some reason, either by thermal stress or by application of externally applied mechanical stress, that crack propagates very fast. Okay. So, it does not get impeded, the motion does not get impeded, whereas if you have a single crystal, there are grain boundaries, and that acts as an arresting point. So, grain boundaries act or restricts the movement of this crack, and therefore, polycrystalline material has a higher strength than polycrystalline ceramics has a higher strength than single crystals. And similar thing also happens in case of glass ceramics. Glass is a basically a uniform or homogeneous material, in which once the crack is generated, it goes through very easily. Whereas, if you have a glass ceramics, that is fine dispersion of second phase crystalline material, that is the definition of glass ceramics. So, you have a matrix, in a matrix of glass, there is a second phase precipitates which are supposed to be hard, and those hard precipitates actually restricts the movement of the cracks through the glass ceramics, and therefore, the glass ceramics becomes tougher than the virgin glass. So, these are some of the basic principles on which one can look at how to strengthen the ceramic materials. These are two basic principles, two techniques by which the movement of the crack can be restricted. Here it is a crack deflection. Okay. Here is a crack deflection in these two examples, and here is a crack breezing, that means some kind of anchoring the crack is taking place, right. So, in this case, if you have a polycrystalline material, large grain polycrystalline material, then there is a crack has been generated between the grain, it is a kind of grain boundary crack, and this grain boundary crack cannot move across the other material, other grain, it has to follow because assuming that the grain boundary region is weaker than the internal grains. So, the crack can grow along the grain boundaries, and because it cannot cross through this grain, it has to deflect. So, this is the deflection of crack at the grain boundaries. So, this is one way of strengthening the ceramics. That is what has been explained, that a single crystal material will have a lower strength than a polycrystalline material because of this crack deflection or restrict the movement of the crack and through. Instead of grain boundaries or grains like this, you can have a different a rod shaped second phase. Okay. If you have a dual phase material, then also you will get what happens in case of glass ceramics we have just discussed, that you have a glass ceramics, you have a presence of a second phase either in the form of a rod or a kind of fiber, or it can be in the form of a particulates, that means a more circular or regular shape particulates. So, in both the cases the cracks has to go through a circuitous route, because it cannot go through directly or in a straight line. Therefore, this is a movement, this is a restriction in the on the path of the crack growth, and therefore, you can also have a strength, higher strength compared to a material which does not have this kind of a second phase dispersion. So, this is the crack deflection method, and then you can also have a crack breaching method, crack breaching technique in fact. So, you can see there is again a second phase, there is a second material coming. This is the matrix is the first page in which the crack is trying to grow. So, in which there is application of load obviously, but then you have some anchoring, maybe some kind of fibers, have been put together or has been dispersed in a matrix of the first phase, and therefore, this is which is restricting the movement of this crack to propagate, and therefore, once again you have a strengthening of the matrix phase. Here also is the same thing. We have fibers, some kind of a fibers which has been restricting the movement of the crack to grow because of the presence of this. The only difference here between these two situations is with no interfacial debonding and with debonding. Debonding means the crack there is an interface between the matrix and this second phase the elongated phases, and because of the application of the mechanical stress, there may be a possibility of debonding at the surface at the interface between the second phase and the matrix. Okay. So, there is a, as you can see here, a very small opening up has taken place. So, that means the cohesive force between this matrix and the second phase is lower than the local stress which is getting generated because of the application of the external force, external stress. So, here it has not taken place. Okay. Such debonding, interfacial debonding has not taken place, but with this the debonding has taken place. So, debonding sometimes is good because some of the energy gets released there. So, for the propagation of the tip, less energy is available. So, by that debonding also one can restrict the propagation of the crack. Okay. So, there may be more deformation, more plastic deformation can take place with this kind of a situation. And here the plastic deformation will be restricted, but its Young's modulus may be enhanced. Okay. So, both these things can be used in a controlled manner to get advantage of the two types of mechanisms. Now, there is another toughening mechanism which is quite different from what we have discussed so far. This is what we call transformation toughening, and particularly in a material like zirconia ZrO2. You may be aware, maybe in some other context we have discussed that ZrO2 has 3 different polymorphic forms. At room temperature it is monoclinic, slightly above room temperature, not slightly above, fairly above room temperature is about 1100 to 1200 degree centigrade. It transforms to a tetragonal phase, and then at a much higher temperature about 2500 or so, 2200 or so, it actually transforms to cubic. So, the cubic phase is normally not stable at room temperature. However, if you add some calcium oxide or yttrium oxide or magnesium oxide, the room temperature, at room temperature the cubic zirconia phase is becoming stable, and that is what we call the stabilized zirconia. So, sufficient amount of either calcium oxide, magnesium oxide or yttrium oxide has to be added, so that the high temperature cubic phase gets stabilized at room temperature, and that is one of the materials used for as an ionic conductor for a different context. But this material also has a very interesting property so far as the mechanical property is concerned. Now, the transformation of monoclinic to zirconia or tetragonal to monoclinic, tetragonal to monoclinic phase is supposed to have a martensitic transformation characteristics. Now, what is martensitic transformation? Martensitic transformation is actually a diffusionless transformation, and it is also called a athermal transformation. Now, so this diffusionless transformation does not really is not a isothermal transformation. So, with time, if we maintain at a particular temperature, it does not the volume fraction does not change, only it is called athermal transformation, that by changing the temperature one can have the transformation. So, these are some of the specific characteristics of this particular tetragonal to monoclinic transformation. In addition, it also had a very interesting characteristics, that the material can be transformed providing through a mechanical stress. So, it is a martensitic transformation or a tetragonal to monoclinic transformation can take place by induction of or stress induced transformation. One can realize a stress mechanically stressed induced transformation. That means, if you apply a stress, it gets transformed, right. Now, it is also associated, this particular transformation is also associated with a fair amount of volume change. Okay. There is a fair amount of volume change at this transformation, okay, just like alpha beta quartz transformation. So, in fact, that volume change is responsible why a lot of crack develops if you try to heat or cool zirconia to this temperature range, pure zirconia to this temperature range, but stabilized zirconia do not have that, because it is more stabilized. There is no monoclinic tetragonal phase transformation. It is stable, the cubic phase is stable throughout the temperature range, and therefore, that kind of crack generation is restricted or can be avoided. Now, zirconia can be toughened. Zirconia, not the pure zirconia or the fully stabilized zirconia, it is basically partially stabilized zirconia. Partially stabilized zirconia, what is called PSZ general, can be toughened by this kind of a phase transformation. What happens in a partially stabilized zirconia is not the complete cubic phase, but it is a mixture of cubic and tetragonal phase. Okay. The fine dispersion, fine structures or the fine dispersions are actually a tetragonal phase. So, that tetragonal phase is again unstable, thermodynamically unstable, and that tetragonal phase can be transformed to a monoclinic phase more stabler form by through a what you call the stress induced. So, transformation here is a stress induced transformation. So, it is not the temperature alone, but the mechanical stress also can induce this transformation, and that is a peculiar characteristics or very important characteristics of this transformation. So, you have you can see the crack is trying to propagate here. You have the matrix phase here, which is basically cubic zirconia, and these are the dispersion phase or metastable tetragonal zirconia particles. Okay. So, the metastable tetragonal zirconia particles are dispersed in a matrix of stabilized zirconia or cubic zirconia. When crack is trying to propagate, it generates a stress field, as you have seen earlier, that it generates a stress field ahead of it. Okay. So, this is the stress field, and within that stress field a martensitically transformed zirconia particles have been formed. That means, which was a metastable tetragonal phase, now it is transformed to a monoclinic phase, okay, because of this stress here. So, as the crack tries to expand or crack tries to move forward, ahead of it there is a strain field or stress field, there is a stress field. Because of this stress field, the tetragonal zirconia, which is metastable in nature, goes back to the monoclinic phase with a volume change. That also generates lot of stress, and sometimes micro cracks are also get developed. So, because of this phase transformation, a compressive stress field around crack tip generates. Okay. So, normally the crack will try to open up with a tensile load. However, because of this transformation and the volume change, and that transformation is also induced by the stress field in ahead of the crack tip. So, everything is quite associated, coordinated or it is a kind of related to each other. Okay. So, you have a metastable phase, and when the crack is trying to propagate, you generate a stress. That stress transforms, a phase transformation takes place of the metastable tetragonal to the stable monoclinic. That transformation also induces some stress, compressive stress, because of the volume change, and as a result everything together, there is a compressive stress created ahead of the crack tip. So, it is a very interesting phenomena which happens in a partially stabilized zirconia phase, and it happens primarily because there is a metastable phase which the transformation is induced by a mechanical stress, not by temperature alone. So, this is what we call the toughening or stress induced transformation, or transformation induced transformation toughening. Okay. So, it is the phase transformation which increases the toughness, and that is why it is transformation toughening in zirconia, particularly in zirconia this kind of thing happens. There are three different forms of zirconia in which this kind of mechanisms are operative. One is, I have discussed already, the partially stabilized zirconia, PSZ. Then there is another material, specially prepared material, which is called tetragonal zirconia polycrystals, which is a pure tetragonal phase. That means, there is no cubic phase. This is partially stabilized because you have a mixture of cubic phase as well as tetragonal phase. That is why it is called partially stabilized. Here it is stabilized, again a metastable phase because it is fully tetragonal phase. There is no sign of cubic phase. So, that can also be prepared by very fine particle size. If the nanometric particle size of zirconia is prepared, it is automatically the tetragonal phase gets stabilized. In fact, it is a metastable phase of course, but room temperature it remains almost indefinitely until unless you stress it. Okay. So, this tetragonal polycrystal the polycrystal of tetragonal also undergoes a similar phase transformation or stress induced transformation when a crack is trying to propagate through this matrix, and that also gets toughened. So, a transformation toughening or stress induced toughening can happen not only in partially stabilized zirconia, but also tetragonal zirconia polycrystals. So, these are the two different materials both based on zirconia, but with different kind of structures. So, that is also a tough material, both of them are tough materials, and there is another group of zirconia related ceramics, which is zirconia toughened ceramics. Okay. Here it is not the matrix of zirconia. Zirconia has been added to other ceramics, maybe alumina, maybe mullite, okay, maybe magnesium oxide. So, the basic matrix is of that of magnesium oxide or aluminum oxide, in which some fraction of zirconia is added, either in the tetragonal form or maybe in the monoclinic form, right. So, they are available there, or the second phase in that alumina matrix of magnesia matrix is basically a metastable metastable tetragonal phase, and whenever a crack is trying to propagate to that phase, again that transformation toughening can take place. In this case, transformation toughening takes place. The matrix is not zirconia, but some of the ceramics, where zirconia is used as a toughening phase. Okay. So, that is called the zirconia toughened ceramics. So, all these things are available and are used in many different applications, particularly zirconia toughened or transformation toughened zirconia is used for many different purposes, including the dyes for wire drawing, even knives. One can make almost like a steel knife made of toughened zirconia. Okay. Paper cutting knives, paper searing knives, scissors, many things are available with toughened zirconia. Of course, toughened zirconia grinding balls, grinding media are also there. So, they are quite tough, at the same time hard. Okay. So, that is transformation toughening. This is metastable tetragonal zirconia particles. Okay. That is what is called the zirconia toughened ceramics. I forgot to mention about these two pictures. We have spent a lot of time on this, but this actually represents the zirconia toughened ceramics, where these grains are of different ceramics, but at the grain boundaries you have tetragonal zirconia. Metastable tetragonal zirconia particles are dispersed, and once they transform, they generate a compressive stress on the surface. Okay. So, this shaded region is actually because of the transformation, this has been transformed to, this part has not been transformed. Open circles means the untransformed, and the closed circles or the solid circles means they have already been transformed because of the stress applied. Once the stress applied from the outside, there is a phase transformation, and that generates a compressive stress on the surface. So, these are the compressive stress area, and these are the normal area. So, because the compressive stress area on the surface, you have difficulty in propagating a crack. So, that is a very important group of materials based on zirconia transformation, and that is why they are called transformation toughening zirconia materials. Well, this is a summary of whatever little already been discussed. The toughening, again the toughening mechanisms, they can be grouped under two groups. One is called the process zone, the other is called the bridging zone. Okay. The different mechanisms to impede the propagation of the cracks, or in other words, the various toughening mechanisms may be classified under two different subgroups, which are schematically depicted here. One is, as I said, it is the process zone toughening, and it is called bridging zone toughening. What is happening here? there are three different concepts or three different principles. You can have micro cracking, phase transformation and crack deflection. This we have not discussed, but if ahead of the crack zone or ahead of the crack tip you have very fine micro cracks. Okay. Somehow because of the stress concentration there, because of the material characteristics, this crack is much larger crack compared to these cracks. So, there are very fine cracks ahead of the crack tip. So, that is what we call micro cracking, and that presence of micro crack also impedes the motion of the main crack or the larger crack, and that is how, because our basic purpose is to impede the motion of the crack, or which is actually giving rise to the failure. So, it is not only the other second phase material, but these micro cracks also generate some compressive stress here, and that compressive stress is not allowing this main crack to propagate. So, this is a micro cracking mechanism which is happening in the process zone in the matrix ahead of the crack. Same thing happening here is a phase transformation, which we have already discussed in details in with reference to zirconia. So, we have metastable phases, they are getting transformed, and that is how you have a compressive zone which is created here. Crack deflection, that also have been discussed earlier, either by the presence of some second phase material or just by grain boundaries, okay, which we have discussed earlier. This is crack deflection either by grain boundaries itself of the same phase or a second phase, either it may be a elongated or a rod like second phase, or even fine particles can also do the same thing. So, these are process zone, that is mean in the material itself where the crack is propagating ahead of the crack zone, that is why it is called process zone, and these are bridging zones. This is the bridging zones mechanism. There is a fiber reinforcement, that means as you know ceramics can be reinforced with different other phases. It can be a fiber, it can be whisker, it can be even a ductile metal bridging. Metals can be used as a reinforcement. So, these are all reinforced materials, right, reinforced materials of primarily fibers, fiber like reinforcement. There can be particle reinforcement here, but here it is a fiber like reinforcement. So, these fibers are actually bridging the crack, it is anchoring the crack not to so that it cannot propagate. Now, you know it is not the monolithic ceramics, but ceramic matrix composites are also quite important, and there has been extensive development so far as the ceramic matrix composites are concerned. One can use different kind of fibers, even ceramic fibers can be used, silicon carbide fibers or silicon carbide whiskers can be used, even alumina fibers can be used as a reinforcement within another ceramic matrix. So, that is called ceramic matrix composites or CMCs, unlike MMCs or metal matrix composites. Ceramics can be used in metals for reinforcement, but ceramics can also be used in ceramics matrix to prepare or to form so called CMCs. One of the major examples of CMC is your carbon-carbon composite, in which the graphite is reinforced with carbon fiber. Okay. So, similarly, there are many different fibers which can be used for reinforcement, and if you have used reinforcement, that is what happens. Either use fiber reinforcement, the cracks will be bridged, and we have discussed that earlier. This kind of crack bridging takes place. Okay. There can be debonding also. here is a whiskers, and you are aware that these are fibers, it is a large size fibers, diameter is larger, and whiskers are much smaller fibrous materials. Okay. Their diameter as well as length are small, and these are ductile metal bridging. Metals can also be used in some of the ceramic composites, particularly an extensive use of metals has been in refractory. Okay. In refractory, metal fibers have been used extensively for reinforcement. So, these are the major mechanisms of toughening. Once we have a toughening by some reinforcement, particularly fiber reinforcement, the stress strain curve also gets modified compared to the original stress strain curve of a monolithic material. This stress strain curve is quite different because of the we are basically delaying or slowing down the crack propagation, and therefore, it behaves little closer to a ductile material. Okay. So, this is the comparison of stress strain diagram of a composite material, metal matrix composite, metal matrix composite compared to the monolithic ceramics. This we have seen earlier. A monolithic ceramics, if you do it under tensile load, it goes up to a point and then suddenly breaks. So, there is no permanent deformation, or ductility is almost nil, whereas if you have a CMC, that means ceramics matrix composite or a reinforcement with some fibers, the stress strain diagram is quite different. It is more like a ductile material. In fact, you do not get any ceramic material like that, what is called the yield point, a kind of yield point phenomena takes place here, the matrix micro cracking stress. Okay. That means, the micro cracking starts here. It is something like a yield point phenomena as we get in ductile material. Then once again it goes, and finally, it with some serrations and it takes fiber pull out, that is debonding actually takes place, more and more debonding takes place here, and therefore, all these serrations comes, and the total amount of permanent deformation before fracture is fairly large compared to almost negligible in case of monolithic ceramics. So, this is a schematic tensile stress strain diagram for a certain ceramic fiber reinforced matrix composite as compared to that of a monolithic ceramics. That is what the comparison has been made. Well, this is the actual evidence of some toughening, what we have discussed, the basic principles we have discussed, and these are the some of the basic schematic diagram of some actual materials. For example, if you add silicon carbide whiskers in different volume percentages to different either ceramics like alumina or mullite or some glass, okay, how the KIC value increases, and you can see the KIC value with the addition of whiskers, the KIC the toughness or the fracture toughness increases quite extensively. Here with 0% whisker, you can see the glass has a fracture toughness of this value. These are of course schematic diagrams, these are not exact values. This is 0 to 12 scale. So, alumina has a higher fracture toughness than mullite and then that of glass, but if you add some percentages of whiskers in it, alumina, the fracture toughness of alumina can be as high as 12, okay, which is very, very high, is almost impossible without addition of any reinforcing agent. Even glass increases not as much as alumina, but it also improves mullite is in between. So, these are the some of the real examples of how the toughness can be increased by reinforcement. Well, there may not be much time, so I do not want to start this discussion of ARCA behavior. That is also another very important phenomena in brittle solids, particularly in ceramics, and maybe we will discuss that in the next class. Okay. So, there are few other points so far as the mechanical behavior is concerned. We will come to that. One is the ARCA behavior, the other will be the Weibull modulus, but since the time is not much there, let me finish for this lecture. So, we will continue this lecture next time. Thank you for your attention.